Okay, folks, this is Lecture 5, and so get in more deeply into assembly language programming and start looking at we'll say the structure of programming, some tricks such as bit masking, and then work a couple examples. And now the next lecture will have a whole bunch of examples. This one is still kind of preliminary stuff. There's very important stuff in here, and I broke it up into multiple lectures just so that there's certainly, I don't have to rush through them like I've been doing with a lot of these. So assembly language, I always love assembly language. It's just like the most fun thing to program in, much more so than higher level languages, and for a couple reasons that I'll mention here. But understand that the assembly languages are a low-level programming language. The assembly language instructions are simply mnemonics. The mnemonics are converted to ones and zeros by the assembler. So once again, the assembler is a piece of software. You're going to write a text file full of assembly language instructions. You're going to send it off to that software. It's going to kick out a file of machine code, which is just a bunch of ones and zeros. Now, the underlying hardware only understands ones and zeros. Those ones and zeros are what is going to control that underlying hardware. So assembly language, I really like working with assembly language for a couple of reasons. One is I'm kind of hardware oriented, and working with assembly language, essentially it's really hard to work with unless you understand the underlying hardware. And I know computer science people who don't understand the hardware that well can still program in it, but I'll say anytime that if you understand that underlying hardware, you're going to be a better assembly language programmer. So generally speaking, it's been known to speed up your programs. So if you know what you're doing and you write your programs in assembly language, technically you can speed your program up. Now the issue is people argue that this isn't the case because we'll say compilers are getting better and smarter, but I disagree. Still, a good human who knows what he or she is doing can write more efficient code than a compiler. Now, a compiler is a program. It's another piece of software that is taking your higher level language and churning out assembly language, and then eventually the assembly language is turned into ones and zeros. Humans can do it better. Good humans who understand the underlying hardware can do it better. So lastly, assembly languages are very tedious. It certainly gives you an appreciation for programming in higher level languages once you've been programming in assembly language for a while. So the bad points of assembly language are the issue of that it's hardware dependent. So it's if you know one assembly language, that's great for that piece of hardware, but it may, it's probably not going to work on another piece of hardware. So different companies, every different products, et cetera, probably have a different assembly language. So you're going to have to learn a new assembly language, which, it's really not that big a deal. It's all about pushing bits around, but learning a new assembly language is a matter of learning the new instructions and how those instructions work together, et cetera. So once you learn one assembly language, the other ones come pretty fast. So once again, if you're not going to write a super long program in assembly language, you're going to use a higher level language. And now the issue is, and I'm going to say this, as far as program speed up goes, one of the tricks that people use is they profile the program they wrote in a higher level language. Typical program spends most of its time in very small parts of the program. So what happens is you figure out where the program's spending most of the time, and you write those parts in assembly language, and therefore you're maximizing your effort because the speed up is going to go to code that's executed most often. So once again, I already mentioned this, that once you learn one assembly language, the other ones come pretty fast because it's just a matter of pushing bits around. So assembly languages, I think one of the reasons I like them is because they're inherently simple. There's just a very limited number of instructions, typically speaking, in assembly languages. Even assembly languages that have a lot of instructions, all the instructions, you can group them together. They still really don't do that much. Okay, but even though there's typically not that many instructions, you can actually do anything with those instructions, particularly with something like we're working with a Lec05a, which is a general purpose instruction set architecture. So the programs, the instructions, yeah, they may not be specific, but you can get things done with them. So another thing in assembly language, what I like about it is essentially you do the same things over and over again. You use the same tricks, and I call them tricks, but they're probably more like constructs. You use the same constructs over and over again. So a typical program is a bunch of these constructs put together in some intelligent fashion such that it solves your problem. Now, my keys to success, or what I think you should do, is learn the tricks. Look, there's not that many of them. We're going to go over a couple of them in this lecture. Know the instruction set. Yeah, there's 40 instructions. That sounds like a lot. Initially, they sound pretty, they look pretty intimidating, but you'll see that there's not, they don't really do that much. A lot of them do the same thing in different ways, and they're very easy to group together. And we saw that before, and we had like I/O instructions, we had number crunching instructions, we had memory related instructions. They fall into just a few groups. So anyway, what I like to do is just give you the tools to get this done, and I'm going to tell you the tricks, and then it's up to you to, take a shot at some of these problems. It's simply very doable. I started working with this over this assembly language over Christmas break, and the idea was, at first it was like, oh my god, I can't do this, and it came pretty fast after that, after I learned this instruction set. So have no doubt you can do it too. So the big picture is you're going to be writing programs. These programs essentially do one thing. They're going to direct the underlying hardware to do something such that it solves your problem. Now, I think this is what problem solving is to me with programs. Is number one, you understand what the problem is, so you know what to do. Once you understand the program, you somehow design a solution, or I say here, generate a path to the solution. The notion here is write pseudocode or a flowchart. I mean, it's always the first step unless your program's like super simple, and I actually have no reason to not do this in these video lectures. I didn't do it on the board because it took extra time, but I'm going to generate flowcharts for all these problems. So once you have the flowchart, what you're going to do is just translate that flowchart into assembly code. Hopefully you've worked with flowcharts. It's not that big a deal. I think there's a section in the book on it. I actually don't have a slide on it because I considered it review. Okay, so the notion here is structured programming. I ask people this all the time, what's structured programming? And they don't know, so I get to use my definition. I think this definition is right. And so structured programming is just a matter of using these same structures over and over again. And the idea is there's only 3 basic structures. So if you can decompose your incredibly long, complicated program all the way down into just these 3 structures, then you have a good program. So if you can't decompose it into these 3 structures, then it's not a good program. Typically it's very fragile, and it's going to be spaghetti code, whatever, hard to maintain, hard to reuse, etc., etc. So structured programs, they work, and they're easy to reuse, maintain, and particularly they're easy to understand. And so we're going to concentrate on writing structured programs. So once again, the structure is sort of these tricks that we're using over and over again, which are very, very simple. not a big deal, and we will mention those here, then we'll hit it later. So these are the three constructs. It's just a sequence construct, which is just nothing really. It's just like do something, which is just a normal instruction. The other construct is the if-else construct. Typically, there's also a case, which is a special version of an if-else construct, and the last construct is iterative constructs. So, two types of iterative constructs that we'll look at. There's actually two other types, but this is all we're going to look at. While loops and do while loops. These are very important. So the while loop is a loop that I enter conditionally, and I may never even enter the loop. And a do while loop is a loop that I do at least one iteration of the loop. And the issue here is, if you look at these, I check the condition first. In a while loop, so I check the condition and I may not even enter the loop. A do while loop, I do something, then I check the condition. So once again, your program should be a conglomeration of these three constructs. If it is, it's a good program. It's going to work right, easy to maintain. Your boss is going to give you big raises here. So anyway, the last point in these things here is these things involve some flow control statements, namely jumps and branches, and that's what we're going to get into in the next slide.